Hi everyone, it is my pleasure today to introduce the speaker, who is Aymen Al Marjani. Aymen is a first year PhD student at ENS Lyon, supervised by Renan Garlivier and Emily Kaufman. He got his master degree in mathematics, vision and learning from ENS Paris-Saclay, with a double degree in statistics from École Polytechnique in Paris. Aymen also spent 6 months at KTH, where he wrote the master thesis under the supervision of Alexandre Proutiere. Aymen is interested in reinforced learning, banded, and sequential statistics. And today he will talk about sample complexity in problem-dependent sample complexity in RL. And with this, the floor is yours, Aymen.
Thank you, Matteo, for your kind presentation.
So, Aymen, you're not sharing your slides.
Yeah, we'll start sharing
okay, thanks.
in a few moments. Do you see my screen?
Yes, thanks.
Cool. Yeah, so thank you for your kind presentation, and thanks also for the RL Theory Seminars team for the invitation. And as Matteo said, I will be presenting this paper, which is a joint work with Alexandre Proutiere, which is entitled Adaptive Sampling for Best Policy Identification in MDPs. So the presentation will be structured as follows. First, we will introduce the setting of our paper. Then we will talk about the lower bound for best policy identification. Then I will introduce an upper bound of we will discuss why the lower bound is not tractable. And then we will present our surrogate upper bound of the characteristic time, which then we will exploit to devise a matching algorithm. Then we will present some experiments and before the conclusion. So why study best policy identification? Simply because we want to know how many samples it takes for a reinforcement learning agent to learn an optimal policy. And I think it's no secret to anyone here that sample efficiency is a very important issue in reinforcement learning applications. So our setting is as follows. So we consider infinite horizon MDPs, which are defined as a tuple, SA, PQ, and gamma. SA are finite state and action spaces. And Q is the reward of the distribution of the reward. So if your agent starts at some state S0, it takes an action, then it receives a reward coming from the distribution Q, which depends on its current state and action. And we will denote by lowercase r the expected reward. Then you have a P, which is the transition kernel, which governs the transition of your agent from its current state to the next state. For simplicity, we will assume that Q has support in 0, 1. In other words, the rewards are normalized, and I think this is a standard assumption, so should not surprise anyone. Finally, gamma is the discounted factor. And we seek to identify a policy, a deterministic one, that maximizes the total discounted reward that goes here. So pi star of phi is simply the policy that maximizes the sum of discounted reward, and the expectation here is taken with respect to the randomness induced by P and Q, the transition and reward kernels. So our first assumption is that pi star of phi is unique. So of course, this is not always the case. I mean, there are many MDPs where you have many optimal policies, but for simplicity, we will assume that it's unique, just in order to understand what are the fundamental challenges of best policy identification before we can later hope for doing epsilon optimal policy identification. So in order to identify the optimal policy, we have many interaction models with the MDP. The first one being the most natural and let's say the most restrictive. It's the forward model. So the agent can start at some state S0 and can only follow the trajectories that are imposed by the dynamics of the MDP. So the agent can only choose the actions. She then receives the rewards, moves to S1, chooses the action, and so on. And in contrast to the forward model, there is another sampling scheme, which is called the generative model, where at each round, the agent can sample any pair. So at round T, it will sample the pair ST80. She will observe the reward and the next state, which are coming from the kernels we defined earlier. And then she can choose any other pair independently of her previous state. So in this talk, we will only focus on best policy identification with the generative model. And the forward model, I would like to say here that it's the topic of an upcoming paper with Aurélien Garivier and Alexandre Proutiere. And it should be available soon in, let's say, the next few weeks. So what does an algorithm consist of? Best policy identification algorithm. It will consist of a sampling rule, which tells you which state and action to sample next, given the history of your observations. And it consists also of a stopping rule, which tells the agent that it has gathered enough information so it can stop and return the empirical optimal policy. And so tau here is the stopping time with respect to the natural filtration of observations. And it will be called the sample complexity. Of course, if the agent stops very early, it may its estimates might be biased, so it might make some errors in predicting or returning the optimal policies. So we require that the algorithm is delta probably correct, which means that the probability that the empirical optimal policy is different from the optimal policy of the true instance is smaller than delta. And of course, we want to identify pi star as fast as possible, which means that we seek delta probably correct algorithms, but which have the smallest or minimal sample complexity tau. Well, in best policy identification, or in usually in let's say reinforcement learning problems, we have two kinds of guarantees, or two ways to quantify the optimality of your algorithm. There is the minimax approach, where you consider a set of MDPs, capital Phi, and you seek the minimal sample complexity over the worst case MDP, which is represented here by the supremum over capital Phi. But one of the drawbacks of the minimax approach, especially in best policy identification, is that they come from pathological examples. For example, the minimax lower bound in best policy identification has a constant Q function for all state action pairs. So real-world scenarios are, of course, different from these pathological cases, unless you're in an adversarial setting, and then it makes sense to consider minimax guarantees. And there's also a second drawback, is that the algorithms that are sample state actions uniformly at random are minimax optimal. So if you only consider minimax lower bounds, then they don't really tell you how to behave and how to design an algorithm that is sample efficient. In contrast to the minimax approach, you have the instance-specific guarantees, where you consider a given instance phi and you try to minimize the expectation of the stopping time tau for this specific instance. So, like to summarize it, if you consider a minimax approach, it means like it is as if you are blind to the hardness of your MDP. So you are considering a lower bound that is constant for all the MDPs, while if you are adopting a more instance specific approach, then maybe MDPs that are easy to learn will take you less time or a smaller number of samples to identify the optimal policy. So we seek algorithms that can adapt to the hardness of the instance. So we look for instance specific bounds and guarantees. So for the related work, the best policy identification with a generative model was first introduced by Kearns and Singh. I think they called the generative model at that time a parallel sampler. Then one of the most important works is the lower bound by Azarial, which gave the following minimax optimal minimax lower bound. And you can already see from this bound that the minimax lower bounds don't distinguish between state action pairs. So in order to learn an epsilon optimal policy, the bound acts as if all state action pairs the kernels of all state action pairs must be estimated to a precision of epsilon multiplied by 1 minus gamma. And of course, there is a variety of minimax optimal algorithms from both families, model-free and model-based. Here are some of the references. On the other hand, for the problem-specific approach, if we consider the simple case of a multi-armed bandit, which is an MDP with gamma with a 0 discount factor and 1 state, then we have multiple papers which provided problem-specific guarantees for their algorithms, and notably bounds that depend on the gaps of the actions. There's also the paper by Garivian Kaufman, which gave a complete characterization of the complexity of best arm identification for exponential family bandits. And in the MDP case, to the best of our knowledge, there's the paper by Zanet et al., which proposed Bespoke. And Bespoke was the first algorithm to provide problem-specific guarantees in the best policy identification. So the principle of Bespoke is to minimize a weighted sum of confidence intervals over state action pairs. It's also called the simulation lemma. And so the starting point of Bespoke is just to try to allocate samples to state action pairs so as to minimize a weighted sum of confidence intervals coming from estimating reward and transition kernels at those state action pairs. Bespoke has many advantages. One of which is that it provides a clear stopping rule to find an epsilon optimal policy, which was not provided by earlier works. Especially a lot of minimax algorithms don't have a stopping rule. They just state that after some number of samples, which is big O of the minimax lower bound, your policy becomes epsilon optimal, but it doesn't specify what's the universal constant behind the big O. And so you don't have an explicit stopping rule for your algorithm to stop and return an epsilon optimal policy. And of course, it provided the first problem-specific bound, which with high probability, the tau is upper bounded by this quantity here, which can be seen as a sum of two terms. The first one is the contribution of the optimal state action pairs, and it scales as the inverse of the minimum gap in the MDP, and the variances, it also depends on which is proportional to the variances of the next state value function after taking an optimal action. The second term is the contribution of suboptimal action pairs, and it scales as the inverse of the gaps of these pairs, and it is proportional to the variance of the next state after taking the pair SA. And so you can already see that there is a difference between the minimax bound and the problem-specific ones here, because the algorithm distinguishes between suboptimal ones and optimal ones. And for the suboptimal state action pairs, we only need to learn them up to a precision of delta and not up to precision of epsilon. But Bespoke has some drawbacks. One of them is that it solves a convex problem at every step to find the allocation it minimizes. So this makes it computationally inefficient. And it has a large burn-in phase. So before starting to iterate and solve their convex program, they allocate a fixed number of samples to every state action pair, which we will see in the experiment section, makes Bespoke less competitive numerically. So
maybe
yes?
I have a question on this slide, just to have a better understanding overall. So in Bespoke, there isn't the assumption of the unique optimal policy. I don't think
no.
Optimal policy, right?
No, they consider the epsilon optimal policy, and the bound I showed here is when you set epsilon smaller than the minimum gap of the MDP.
Okay.
So if you set epsilon to be something smaller than the minimum gap, then an epsilon optimal policy becomes the optimal policy.
Mm-hmm. Okay, thanks.
Okay.
So wait, maybe that's a dumb question, but like, what is the definition of this delta mean and this delta SA?
Delta mean is the minimum gap of the should be somewhere along the slides. So the delta mean is the minimum gap of the MDP. So it's the delta SA is difference between the value function at state S minus the Q function of the pair SA.
Right.
And
it's like the advantage function.
The data mean is the minimum over all possible S, or like?
No, it's the minimum over suboptimal action pairs, state action pairs.
So okay, all right. So it's the action gap is the minimum action gap, and it's only for the positive action gaps. Okay.
Yes, exactly. It's always positive. It's only for the suboptimal ones. So.
Okay.
Yeah. So before we try to devise an algorithm, we have to know what to aim for or what we can hope for. So it makes sense to start with an information theoretical lower bound. Now, before introducing our bound, we need a few definitions. So we define the set of alternative MDPs, which is simply the MDPs psi, where pi star is no more optimal. So recall that pi star was the optimal policy in the MDP phi. So the alternative set is the set of MDPs where psi is no more optimal. We define sigma to be simply the simplex over state action pairs. And the KL divergence between phi and psi at state as at the pair SA is simply the sum of KL divergences between reward kernels and the KL divergence between transition kernels at the pair SA. And so using classical change of measure arguments, we develop our first lower bound for all delta probably correct algorithms. So our first result states that the expected sample complexity for any delta probably correct algorithm is something like log 1 over delta multiplied by characteristic time, where the characteristic time is a quantity that characterizes the hardness of the instance. Yes, so this characteristic time might seem odd a bit for people who are not familiar with the change of measure. So one common interpretation of it is that it can be seen as a two-player zero-sum game between your algorithm and nature. So your algorithm, which is the blue here, chooses a sampling strategy, omega, in the simplex, and nature will pick an alternative instance, psi, which is hard to distinguish from phi under this sampling strategy. So for a fixed sampling strategy, omega, nature will try to pick the most difficult alternative instance to distinguish statistically from phi. And so your algorithm, in order to be delta correct, cannot stop unless it has gathered enough information to distinguish phi from all the alternative instances psi.
So maybe a quick question. I mean, honestly, two questions.
Yeah.
One, if I missed it, there is any assumption on the MDP like ergodicity or communicating MDP, or can be anything? And the second question is whether you are considering structured instances or unstructured, so tabular versus can be any type of structure fee.
Okay. Yeah, so I'll start by answering the second question. We only consider unstructured MDP, so tabular MDP with no assumptions on the structure. And for the first question, there is no assumptions on the ergodicity of the MDP because we are considering a generative model, which says that at any time step, your algorithm can sample any state action pairs independently of its previous state. So your agent or your algorithm is not constrained by the dynamics of the MDP. It's like it has access to a simulator that will simulate plain action A at state S. So we don't need any assumptions on the ergodicity or communicative properties of the MDP.
Right. Sorry, I missed the part of being the assumption of having a generative model.
Yeah, sure. No worries. So yeah, the first intuition is try to solve the lower bound program here in order to get what's an optimal delta probably correct sampling strategy, and then maybe you can come up with the algorithms to track or to achieve this lower bound. Yes. So for starters, the set of alternative instances by definition is defined as all instances psi such that there exists a state S and a policy pi where the value of this policy pi becomes larger than the value of pi star. This is just the definition of alternative instances. So this definition involves too many parameters of psi. So mainly the condition here on the value functions would involve all the mean rewards and transition kernels at the trajectory of policy pi and at the trajectory of policy pi star. So if you're trying to solve this lower bound program here, where the objective is the KL, so you have too many parameters. So our first step towards solving this problem is to simplify this set, which sorry?
No, I think there was no question at all.
Okay. Yeah, so this led to our first lemma here, which decomposes the set of alternative MDPs as follows. So instead of having a condition, a global condition on policies here, we have a local condition on the Q function and the V function. So this lemma just states that an alternative MDP psi is simply an MDP where you take the any suboptimal action, then it will have a larger value than the value function at state S. This is in contrast with the case for phi, where you have the reverse inequality. And this lemma allows us to reduce the number of parameters. So instead of optimizing over kernels at true policies, we have to optimize only over the kernels at SA and the kernels at pi star. But it turns out that this information theoretical lower bound, or this characteristic time, is intractable, and you can actually easily construct instances where you show that this set of alternative MDPs is not convex, nor these subsets here, which are shown in the condition. So you can consider an MDP with two states, S1 and S2. So you start at state S1, and once you arrive at state S2, then the state is absorbing, so you stay there and you get 0 reward. The arrows, dashed arrows, correspond to the first action, A1, and continuous lines correspond to action A2. And we have all these fixed parameters of the MDP here. So what you can change in this class of MDPs is only the reward by action A1, the transition, the probability of staying at state S1 after taking A1, and the reward of the action H, the second action. So in this section, it's easy to see that the Q function has this nice expression here, depending on the rewards and the transitions. And you can easily come up with numerical values for R1, P1, and R2, such that you have two instances where the action A1 is the optimal action, but the average of these instances have the action A1 as a suboptimal, and the A2 becomes optimal in the average. So what this shows is that these sets alternative set of instances phi, and the subset where action A1 is optimal or becomes optimal are not convex. And so consequently, the sub-problem that defines the characteristic time is non-convex.
So sorry, maybe
yes.
A trivial question. So
yes.
just a better understanding of this inferior, how to solve this inferior. So the inferior poses a constraint on the optimal policy. So you need to verify the inequality involving the Q function under the optimal policy. And the problem why is not easy to solve is that you also need to solve this linear constraint, but where the variable that you are optimizing compared to a normal problem are both transition model, because you need to consider alternative set, but also the value function, because you need to solve for the optimal policy in this alternative set. Is a right interpretation of why this alternative set is complicated to solve?
Yes. It's not because you have. It's not the sets are not convex because we have too many parameters, but because of, as you said, the shape of the value function is not straightforward, or let's say the value function depends in a non-trivial way on the rewards and the transitions, which are the natural parameters of the MDP. So here we are considering this infimum problem where the objective is convex in the parameters Q and pi, or R and pi alternatively, but the shape of the value function, which is the constraint that on the alternative set is not straightforward. Yeah, so here is like a simple comparison between the multi-armed bandage case and the MDPs. So in the multi-armed bandage, where we have mean rewards mu1 to mu k, and the objective is to identify the optimal action. The optimal action depends in a simple way on the parameters of the bandage instance. So it's defined as the argmax of the mean rewards. This allows you to decompose the set of alternative instances into a union of convex sets over which you can compute the information theoretical lower bound. But in the case of the MDPs, the optimal policy depends in a non-trivial way on the transitions and the rewards here. And so this makes the constraints that define the alternative set non-convex, which makes the lower bound problem intractable.
Can I ask a question about distractibility?
Yes.
So just because something doesn't have the structure that we are happy with doesn't necessarily mean that it's intractable?
Yeah, sure. But even for a small instance with 2 states and 2 actions, you can clearly see that the problem is not convex.
Sure.
And maybe you can say that
are there not non-convex problems which are tractable? I think they are.
To say a bit of a controversial remark, I guess we're being recorded, but I'll say it anyway. Isn't one of the big lessons of deep learning and deep neural networks the fact that there is a very large amount of non-convex optimization problems that can nonetheless be solved good enough?
Oh, yeah, like I can turn that into an even more constructive comment / question, which is that, is it enough to calculate the optimal solution up to constant factor approximation in this case to get some good result at the end, or do we have to have like absolute precision or whatnot? Like later I need to plug this into the solution of this into an algorithm, I suppose. But maybe you don't actually need to solve this up to a high accuracy. And
yes. So you're saying that we can find like near optimal allocation strategy, and
potentially, and then maybe that's tractable.
But then the question would be, how do you get guarantees on the near optimality of your allocation strategy?
Design an algorithm, prove it. I don't know. I didn't do the work. I'm just curious about. Okay, so this is the definite question that crossed my mind.
Yeah.
If we have a constant approximation, so up to a factor of 2, like I was able to compute the optimal allocation in this problem. Does it mean that like the bigger problem can be solved, like with the required sample complexity up to constant factor approximation?
So what I mean, how do you define a constant? You're saying the allocation is optimal up to a constant factor?
It's like you try to
characteristic time, I guess you want to say. You get a two approximation of the characteristic time with a certain allocation.
Yeah, that's right.
This is a little bit what we are doing in this work. Actually, we are.
Okay. So we're jumping ahead. All right. So then maybe the conclusion is not that like this is so intractable we can't do anything, but it's like there is no obvious way of dealing with this thing because it's non-convex. So it's like the trivial solution that we just use convexity is not going to work.
Yes. So yeah, we can phrase it that way.
All right. Okay. Good. Yeah. Good.
Yeah. So we say that the problem is not tractable. What we mean is that you have here an objective function that is convex in the parameters, and the constant is not the constraint is not convex. Maybe you can use a deep learning, some sort of deep learning network to optimize over it, but then the problem would be to have guarantees that the allocation you get is sufficiently near optimal. So I'm not aware of any guarantees that over the optimization error for deep learning, but maybe it could be an idea. So our next proposition or idea is to find an upper bound surrogate of this characteristic time here, which we'll use to derive a near optimal allocation, then to devise an algorithm. So to summarize what we have presented so far, if you put phi at the origin of your of this figure here, you got the set of alternative instances, which is the shaded area, and it has a non-convex boundary. So our idea is to study a KL ball that is inside this boundary here. So we are kind of looking for a larger set that includes the set of alternative MDPs. So basically, all the instances here, which are outside of this KL ball, will, this set will include the set of alternative MDPs. And so our main result, or first result, is this one. It's an upper bound on this characteristic time. And it is the sum of two components. The first is the contribution of suboptimal state actions, and the second is the contribution of the optimal pairs. So the contribution of suboptimal state action pairs is made of terms T1 and T2. So term T1 can be interpreted as the cost to learn the reward kernel, and T2 is the cost to learn the transition kernel. Then terms T3 and T4 are the same. So T3 is the cost to learn the rewards at optimal states, optimal pairs, and T4, well, it has an ugly expression that you can check on the paper, but the main important thing about it is that it's always smaller than the minimax lower bound divided by number of states multiplied by number of actions. And so you can see here that all these terms are big O of the minimax lower bound divided by SA. And so you can see that an algorithm that samples states and actions uniformly at random. So omega is 1 over SA for all pairs. You can see that through this naive allocation, you can still be minimax optimal. So what do we conclude from this? We can conclude that an algorithm that samples according to some less naive allocation and preferably the optimal allocation will definitely do better than the minimax lower bound. Is it clear by now the upper bound and the terms? So if it's clear, I will move on. So yeah, I think it's interesting to present a sketch of the proof of this upper bound. So recall that using lemma 2, we reduced the number of parameters in the optimization problem that defines the characteristic time. So using this lemma 2, we can rewrite the definition of the characteristic time as follows, where here we don't have a sum over all state actions, but only sum of KL divergences at SA and at the trajectory of the of pi star, the optimal policy. Next, we introduce the sub-optimality gaps of the MDP, which are defined as follows, and we rewrite the condition above for the alternative instances as follows. So the difference in Q function between psi and phi in state SA minus the difference in the value function between psi and phi is larger than the gap. This is just a reformulation of this condition here. It's just a basic algebra. Next, what we do is that from this condition here that we have here, we can already see that to construct an alternative instance, you have to move your or you have to change your reward or transition kernels by a minimal amount. So what we try to do is to use the Bellman equation to make appear the differences in rewards and transitions. So using Bellman equation, we rewrite the condition as follows. dr and d of p is just the difference in mean rewards and difference in the transitions. And d of v is the difference in the value function. This term here is a bit still more complex, so we will decompose it further into two terms. So the difference in value function can be composed into a and plus b. So a is just the difference that comes from changing the rewards at the optimal policy, and b is the difference that comes from changing the transition kernels. So yeah, from this condition here on the kernels, we can deduce that you have at least to change your rewards transitions in such a way that the sum is larger than the sub-optimality gap of SA. So you can write each of these terms as a proportion of the gap with the sum of these proportions larger to 1. Then you can we use Pinsker inequality and transportation lemmas to relate the difference in kernels through the KL divergences. So for instance, for the first term here, dr, you can simply use just Pinsker inequality and you get this this bound here. And similarly, similarly, you have these bounds that come from from using information theoretical inequalities and from the fact that we wrote these difference in kernels as proportions of the sub-optimality gap. Then you sum up these bounds, which we have here, and then you optimize over alpha. which means that for this condition here to hold, there exists an alpha such that the sum of alphas is larger than 1. So here you try to find what is the infimum over alphas of these the sum of these individual lower bounds. And so you can see that from summing this lower bound and optimizing over alpha, you would get a lower bound of this quantity here, which is the inverse of the characteristic time, and this will naturally translate to an upper bound of the characteristic time.
So wait, I got lost. What is T1, T2, T3, T4, and why did they pop up in these inequalities?
Okay, so T1, the terms are defined here. So T1 is something like the inverse gap squared. T2 is variance over gap squared. T3 is the same thing, but over the minimum gap and with a factor of 1 minus gamma. And T4 has a complicated expression, but you can say that it scales at most as this quantity here. And so where they come up at the proof, so it's just they come when you try to relate these terms here, dr, d of p, a, and b, to the KL divergences. So we use transportation lemmas. For example, for the second term here, we use a transportation lemma that relates this the difference in kernel transposed to the value function. We relate it to the KL of the transition kernels at state SA, multiplied by some quantity which scales as the variance of the value function after taking the pair SA. So this term T1 to T4, they come from Pinsker plus some transportation lemmas to relate the difference in kernels to the KL divergence between these kernels.
All right, yeah, that makes sense. Thank you.
Okay, so once you sum up these lower bounds, as I said, and optimize over alpha, you get a lower bound of the inverse of T of the characteristic time, which translates into the upper bound we presented in theorem 1. So now that we have a surrogate of the characteristic time, or an upper bound of the characteristic time, we can try to devise an algorithm
Sorry, yes? There is a question. I mean, it's very specific, but maybe you can answer now. There is a question about the definition in term T2.
Yes, sure.
There is a notation related to
this term, OSC.
Yeah, what does it represent? Is something related to higher order moments?
It's the oscillation of the value function. So, or like the span, if you prefer, it's the span of the value function.
Okay, got it. Thanks. So maybe another question related to this upper bound. It seems that one of the key ingredients in obtaining this result is that when you consider the inferior over the alternative set, you can decompose it, or at least you can focus on a single, an independent state action pair, right?
Definitely, yes.
These, not normally you obtain these when you do lower bound for gratinization because you consider ergodic Mdps and so on and so forth. You can concentrate on individual terms. Here is mostly because you are considering a generative model. The fact that you can decompose individual states.
No, actually the decomposition holds independently of the generative model or the forward model. So the decomposition that comes from lemma 2, sorry, where is it? Somewhere here. Yeah, so this decomposition here holds for all MDPs. It just uses the fact that the Bellman operator is how do you say that? Is monotonous. So you can prove this by contradiction. So if you make one suboptimal action larger than the value of that state, then necessarily you can construct a policy where a policy, let's say p prime, which has a value larger than pi star, and it doesn't really involve the generative model.
Okay. Okay, thanks.
The generative model comes in the lower bound, as I said before. So we can have this supremum over the simplex because of the generative model. So because we are not constrained in the states we sample, we can reach for all allocation vectors in the simplex. Whereas if you had a forward model, then you need some assumptions about the structure of your MDP and the ergodicity to know what are the achievable allocation vectors. Yeah.
Okay, makes sense. Thanks.
So yeah, to continue from where I was saying, so now that we have this nice explicit upper bound here of the characteristic time, we can use it to derive an optimal, an algorithm that achieves this upper bound. Yeah, so first of all, the optimal weights that minimize the upper bound are easy to compute. So we have a closed form expression for them. They scale something like this. So for example, for a suboptimal pair, it would scale as the variance of the value function after taking action A at state S, and they are inversely proportional to the squared gap. So this is natural because the more the state SA is suboptimal, the larger the gap. So we need to sample it less in order to know that it is suboptimal, so we can identify the optimal policy. Similarly, for the optimal pairs, they are sampled as, the expression is roughly speaking the maximum variance along the trajectory of the optimal policy divided by the gap squared multiplied by 1 minus gamma squared. The 1 minus gamma comes because the effect of optimal pairs propagates through all the chain, whereas for suboptimal pairs we don't have a term of 1 minus gamma, because if you have let's say an error of estimation for the kernels at state SA, they don't necessarily propagate to the value function, so you only need to learn them up to a precision of their gap. So for our sampling rule, we will use the C-tracking, which was proposed by Gary and Kaufman. So simply you take the optimal allocation vector and you project it on this subset of the simplex, where you impose that each component is larger than something that looks like 1 over square root of t. So this projection here is just to ensure or enforce exploration, so that if you start with bad initial estimates and your overline omega is close to 0, you don't end up leaving state action SA while it might be optimal, and you just missed it because you had bad initial estimates. And once you have this projection, then what you do is that you the next state you sample is the one that has been visited very few times compared to the cumulated sum of the optimal allocation vectors over the history of your sampling.
There a multiplication with total number of samples missing there, or like the scales of this number of samples and frequencies are they the same, or am I just confusing myself? Oh, there is a sum. There is a sum.
Yeah, there's a sum actually.
1 to t. Oh, okay. So it's like
so basically they scale alike.
I see.
Yeah, so the idea is that you have these estimates of your optimal allocation here. You sum them over all the empirical MDPs you had from your history. Then you see the state action which really lags behind this this cumulated sum of optimal vectors. Then you will sample it in order to correct this this difference here.
Yeah, and I guess this has some smoothing effect as opposed to just using the most recent model and then multiplying with t. Would that also work, or that wouldn't work, or we don't know?
Yeah, there's the what you're referring to is called the detracking, where you just sample the one that lags behind the actual estimate. So instead of a sum here, you only have the optimal the optimal vector of the white height of t. So yes, it would work. It would work for having a bound on the stopping time with with the probability 1, so almost your upper bound. But I'm not sure it would work to have a bound on the expectation of tau, of the sample complexity. And besides, as you mentioned, it has a smoothing effect. So when you are considering this sum here, it kind of stabilizes your the vector, the allocation vector you are trying to reach. Versus if you delete the sum, then maybe your estimates might change quickly, and then your sampling strategy will not be so stable.
Interesting.
Okay, so the main advantage of this sampling rule is that it ensures that with the probability 1, the sampling frequencies of your state actions converge to the optimal allocation vector of the true instance. And so the second ingredient of our algorithm, called KL ball track and stop, is the stopping rule. So recall this figure that we had before, and now at the origin you put the empirical instance wide hat of phi. So in order to make sure that the optimal policy in the empirical MDP equals the optimal policy of the true instance, it is sufficient to check that phi falls within this KL ball here with probability 1 minus delta. So if phi falls in this ball, then we are sure that phi and phi hat share the same optimal policy, and so we can stop and return the empirical optimal policy. And to do this, we just use the standard concentration or deviation inequalities on KL divergences from the literature. So combining this the sampling rule here and the stopping rule, we get the KL ball track and stop, which enjoys the following guarantees. So for all values of delta, the expectation of your stopping time is finite. You can, yes, so the expectation of the stopping time is finite. And as you check delta to 0, then the expectation of tau is smaller than log 1 over delta multiplied by 4 times the upper bound phi, where this upper bound is just simply the supremum over all allocations of the surrogate we presented in theorem 1. So that's the guarantee. And one thing that is interesting is to see how this upper bound scales with the functionals of the MDP. So let's say the measure or the leading terms of the upper bounds are the following. The first one represents the contribution of optimal state action pairs. It scales like this. So S times multiplied by the maximum variance along the trajectory of pi star divided by the minimum gap 1 minus gamma square. So either this or the usual minimax lower bound. And the contribution of suboptimal pairs scales like the variance of the value function divided by the gaps of these state action pairs. So you can see that this bound here is problem specific, depends on functionals of the MDP such as the gaps or the variances. And it has the nice property that, as we said earlier, the omega that solves the supremum here is explicit, and we have a closed form expression for it. So now we move to the experiments. The first experiment is just trying to show that theorem 3 holds numerically. So basically, the red line asymptotic bound here is just 4 times the bound u of phi multiplied by log 1 over delta. And this is the stopping time of the algorithm in blue, where we plotted the shaded area is the 2 times the standard deviation. So we see that as delta goes to 0, the stopping time goes below this bound here. This was for a randomly generated MDP with 2 states and 2 actions. Now for the second experiment, we compare...
by the asymptotic bound, is it the upper bound or the lower bound?
The upper bound, so 4 times u of phi multiplied by log 1 over delta.
Okay.
So yeah, the second experiment is comparing KL ball track and stop with bespoke. So in the y-axis you have the sample complexity on the log scale, and so we see that clearly that KL ball track and stop outperforms bespoke by several orders of magnitude. And the shaded area has shrinked here because of the log scale. We do the same, but for a larger instance, so 5 actions and 10 actions per state. And we only plotted for bespoke here. We only plotted the burn-in phase number of sample. So recall that we said the bespoke start by allocating a constant number of samples to all state action pairs. Then after having its first initial estimate based on this burn-in phase, it starts iterating over a program. So we only computed this burn-in phase number of samples, and we can compare it with the total stopping time of KL ball track and stop. And here again, KL ball track and stop outperforms bespoke. But note that Yeah, here we used only delta from 0, 1 to 10 to the power minus 3. So it's a smaller scale. And we don't see the convergence of scalable track and stop to its asymptotic bound yet because of this small scale. Yeah, so as a conclusion, algorithms designed to using problem-specific bounds can do better than one for best policy identification than ones that use minimax bounds. As we said earlier, sampling randomly state actions uniformly at random makes you minimax optimal. So you can definitely do better by having a much smarter sampling strategy. Second conclusion is that contrary to the bandage, the IT lower bound is intractable for MDPs. But we can derive problem-specific surrogates which are explicit and have easy to compute optimal allocation. And this in turn can be used to divide an algorithm that matches this surrogate upper bound up to some constant. Yeah, so this work was the first step towards understanding problem-specific epsilon optimal policy and identification. So thanks for your time. I hope I respected the limits.
Yes, quite a bit. Thank you.
Thank you.
Thanks, Aymen, for the presentation. Maybe question just in terms of comparison between your result and bespoke.
Yes.
It's that one difference that you stress is the burning time of bespoke. For the rest, there are other significant differences between the bound that you get and the one of bespoke. Maybe I missed that part.
I think the bounds scales similarly.
Okay.
So if we go to yeah, so the bound of bespoke is here. So with high probability, you have this nice bound. Depends on the variances, gaps, and so on. So other than the constant term, I think they are quite similar with two differences. So the first difference is that this bound holds with probability 1 minus delta. So maybe a tau can be infinite on the failure event. Versus a scalable track and stop, we control the expectation of the stopping time, and so we show that it's finite. So your stopping time is finite almost surely. The second difference is that we have some terms here like this span of the value function to the power 4 over 3. So this second term here in T2 and which appears also in T4 does not appear in the bound of bespoke. But the leading term is always this one. I mean, in almost all of the experiments we did, the leading term of the bound is the variance over the gap squared. So it's practically the same as for bespoke.
Okay.
I don't know if I have answered your question.
No, you have, yeah. Thanks.
So I have a similar question regarding like what are really the leading terms in your bounds. So if you just go to your final bound on the sample complexity, then there's this term that is the maximum between the variance and this other term.
Yes.
So maybe I just didn't think about this enough, but to me it seems that the second term is always bigger than the first one, or no, or is this like a function of the reward scale, or like can you explain a little bit what I'm missing?
It's a function of the variances.
Mm-hmm.
So the worst case variance would be 1 over minus gamma square. So the first term would be smaller than the second term.
Oh yeah, right. Yeah. Sorry, it was that
But
second
if
power
you're
of the 1 minus gamma times. Yeah. Right. I see now. All right. Good. And then I guess like further along the lines of comparisons with bespoke, like you said that, well, that algorithm is like complicated to implement, or you're somehow suggesting that it's not very practical because it has to solve a convex problem in each round, but it's like a convex minimization problem, and like how easy it is to optimize that actually.
Yeah, so they solve a convex optimization program. I think in their paper they provided an efficient algebraic formulation of their program to solve it. But still, if you're considering large instances, then the computational complexity of bespoke blows up. So versus in the case of K-ball track and stop, you have a explicit or closed form expression for the optimal weights.
Right, I see. No, it just kind of like, strange to contrast this with your claim that the actual characteristic times are intractable because they are not convex, and that is contrasted with this other convex problem that they are solving. But turns out that even if it's convex, it's not really tractable.
Yes, I mean there's definitely a trade-off there in this lower bound between the computational and statistical complexity. So if you're trying to be very sample efficient, then maybe you need an oracle that solves non-convex programs. And maybe if you're willing to sacrifice some of the statistical efficiency, then you get some smaller computational complexity.
Yeah, so like maybe more on this front. Yeah, so here you were suggesting that, well, the fact that, well, this is not convex in this parametrization makes this problem hard.
Yes.
But that fact does not mean that there does not exist a parametrization in which it would be convex, right? So just because in this concrete formulation you're facing a non-convex problem, it doesn't imply that there doesn't exist.
I mean, mathematically speaking, yes, I agree with you. Like mathematically speaking, there could be some formulation when the problem becomes convex, but I hardly doubt so, because you have a convex objective in terms of the kernels, and the constraints are not convex. And they're not convex for very simple reasons. So if you ignore this inverse matrix here, you just take this, like suppose your problem is convex in this inverse matrix here. Just the fact that you have this product of rewards by this discounting matrix makes it non-convex.
Yes.
So actually, in our example here, we really just rely on the fact that you have this reward here multiplied by the inverse of this. So just by this very simple fact, you can make your problem non-convex. So I would really doubt that you can change the parameterization and find a convex formulation, but
Right. So even if it's linear in this 1 minus gamma p, well, the product actually becomes bilinear, which is not convex, and that's right. I can see that.
But if you can come up with a convex formulation, I would be happy to.
Yeah, very interesting. Very nice. All right, so maybe there are some other questions by other side.
Yeah, I still have a couple of questions. One is about the connection with the lower bound, the derivation of the lower bound, that requires, at least for the way we know how to drive this lower bound, to have a unique policy. Do you have any insight whether this condition of uniqueness of the optimal policy is relevant or can be can be relaxed, there is a different possible way of deriving the lower bound. I know that it's kind of common to have this assumption, just to know if you have any insight on that aspect.
Yeah, so for epsilon optimal policies, I think, yeah, maybe you can derive bounds, but it's it's not easy. I mean, even in the case of multi-armed bandage, the problem-specific lower bound that comes from the change of measure becomes more complicated, because you have to test for multiple hypotheses. So if you're looking for an optimal the optimal policy, you're just testing two hypotheses. This policy is the optimal one or is not. Versus when you test whether a policy is epsilon optimal, you can have many so you can have many epsilon optimal policies. So you have to test. You have multiple tests. There can be instances where this policy pi1 is epsilon optimal and pi2 is no more is not epsilon optimal, and vice versa. So you have multiple tests, and this makes the lower bound more complicated. So I would suggest the paper asymptotically optimal hypothesis testing by Garivia and Kaufman in 2019, and it reads the case of epsilon optimal best arm identification, and you can already see that in that case the lower bound becomes more complicated. Yeah, the paper is called Non-Asymptotic Sequential Tests for Overlapping Hypotheses, an application to near optimal or best arm identification. I don't know if I have access to the chat. Maybe I can.
Okay, thanks a lot. And the second question is maybe about the generative model assumption. So
Yes.
is it possible to be removed? What are the complications of removing the assumption and being fully online?
Can you rephrase that, please?
I mean, now you're considering the case in which you have a generative model, so you can sample any state. But if you want to go full online, is it possible to remove this assumption? What will be the complication there?
Yeah. So this is the topic of an upcoming paper. So basically, what would change in your lower bound is sorry, I'm having trouble to share my screen, so just gonna do So can you see the slides?
We can see the paper on non-asymptotic sequential.
Yeah, I shared the wrong. Yeah, so please hold with me. For some reason, I can't stop sharing. Yeah, but basically, what changes in the case where you don't have a generative model is that you cannot reach all the allocation vectors in the simplex because you have constraints by the dynamics of the MDP. So you have only a subset of the allocation vectors which are achievable. And yeah, so this makes the problem a lot more harder because you cannot find the optimal allocation, let's say, easily. Maybe Alexandre has a better understanding of this Then
you did it well. I think the problem is the optimal allocation. It constrains to the dynamics, so you have to follow the dynamics of the systems, which poses a problem in terms of tracking the optimal allocation. So it's and in addition, we are not sure about how to include mixing properties in the lower bounds, for example. So if you look at the lower bounds as they are derived right now, they don't really include mixing properties of the dynamics of the system. So it's also kind of open to try to derive lower bounds that accounts for that. There are some papers in the there is a paper in NeurIPS last year about what was it called? Regression under Markovian data, and so we have exactly the same kind of problems. And you observe you have Markovian data, you don't have IID data, and this essentially brings the dynamics of the system into the lower bound, and you have to take care of that. So it's more complex and interesting in a sense.
Yeah.
And the usual techniques usually do not account for that because they are asymptotic, and so they don't capture mixing properties of the dynamics typically. That's
and normally they also consider ergodic Mdps. At least the lower bound from Burnett-Skatiakis is for ergodic Mdps.
Yeah, but absolutely, yeah. But that's for that's true. Yeah, in a sense, if you compare to the studies that have been made in regret minimization, there you have kind of MDPs which essentially erase all mixing problems.
Yeah, exactly.